Okay, so this time we'll talk about how to find a particular solution for some specific g of t. Not all form of g of t are solvable, but yeah, we here list some of the function for g of t so that we can guess the solution out. The guess means later on you probably need to remember how it formed. Okay, so yeah, there are polynomial, exponential, sinusoidal. Okay, for the sinusoidal, it means sine, cosine, or maybe they occurs together, but not for tangent, because tangent will go to infinity, which is not usually occur in the daily life. And for 4, 5, and 6, they may be 2 of them combined together, or even 3 of them combined together. Okay, so out of these types, so probably you need Fourier transform or Laplace transform for solving other form. Still not all the form we can guess the solution, but yeah, maybe for some of the form, yeah, we cannot use this, but maybe Laplace transform can help you. But yeah, actually you need to learn more mathematics for the Laplace transform later. But so here we only limit to here. Okay, so for first one, which is the simplest case, I think. So it is for polynomials, 多项式. Okay, so you should know a polynomial Pn of t should be like Pn of t should be like an something like an t to the nth, and then a minus 1 times t to the n minus 1 power, and then all the way up, all the way down to a sub 0. So it's the nth order polynomial. And of course, for the most simplest case is a zero order 1. Yes, a specific case is like 0th order of polynomial, which means this is a constant. It is a constant. So which usually occurred. Okay, so yeah, so here it says if g of t is a nth order polynomial, we denote it as a Pn of t, then we can assume the particular solution to be also an nth order polynomial. So let's see what it means. So here's an example. So this is the second derivative minus 2 times the first derivative minus 3 times the original function, and then equals 40 minus 5. So this is a first order polynomial. So this is first order. So for the first step to solve it is to find the homogeneous solution. So always need to find the homogeneous solution first. So yeah, so we just make the right hand side to be 0. So we have, this is the left side equals 0. Okay, so in this case, you can write the characteristic equation, which is second derivative s squared minus 2 times the first derivative, so 2s, and then minus 3x. So this is the 0 derivative. We change it to 1, so minus 3. Okay, equals 0. This is the characteristic polynomial, or the characteristic equation. So solving this one, we can get s equals -1 and 3, s to be -1 or 3. Okay, so we get exponential to minus t, and then make exponential to 3t. And then this is the linear combination of these two solutions. Okay, so this is the first step to find the homogeneous solution, or the complementary solution. And then the second step is to guess, or maybe you should remember the form. Okay, so here we have a first order polynomial of t. So xp should also be another first order polynomial of t. So we make it a plus bt. And then we just substitute this one back to the differential equation we like to solve. So here, this is the function, second derivative minus 2 times the first derivative minus 3 times the original function equals 40 minus 5. So here we just plug in this one to here, here, and here. So we get this 1, 2, 3 times. So the second derivative of a first order polynomial is 0. So this, so this is nothing but 0. And then the first derivative of this one should be, this is a constant. So first derivative is 0. And then this is bt. The first derivative is b. So we have, this is minus 2b, which is this one. And then this is the original function. So minus 3a minus 3bt. So minus 3a minus 3bt. And then equals this one. So we just collect the term. This is the first order term. So here we put it here. And then this is the constant. So we have minus 3 and minus 2b here. So equals to 40 minus 5. Okay, so for these two first order polynomial of t, if they are equal to each other, which means that the coefficient should be equal, which means that minus 3b should be the same as 4. So we have this one, and then minus 3a minus 2b should be negative 5. We have the second equation. So here we have two unknown with two equations, which means that we can determine the unique solution if they are not dependent. But yeah, so for this case, they will not be independent, unless there may be some case that no solution. But yeah, not for this one. Okay, so maybe so at least this one we can get the solution. A to be 23 over 9, and then B equals negative 4 over 3. Okay, so we plug these two numbers back to here, which is the particular solution. So this part is the particular solution. This is xp, this is xp, this is xc. Maybe you can also write as xc of t, xp of t. Okay, so just the first step is very easy. You just add them together. So this is the complete solution. This is the complete solution. So when you just see the constant coefficient ODE, 3 steps. First step is to find the homogeneous solution. Let the right hand side to be 0 and solve it. Okay, and then the second step, assume the particular solution, and then find the unknown coefficient. And then finally you add them together. Just that easy. Okay, so so now you can determine the unknown coefficient for xp, but you cannot determine C1 and C2 because you don't have the initial condition. Sometimes we may have the initial condition, but if we don't have this initial condition like here, then we cannot determine C1 and C2, which means that for arbitrary C1 or C2, all of it are the solution to this one. You can just check it by yourself because last time we already know if we just put this one back to the left side, it will be 0. So, and as much as this is linear, so when you multiply by an arbitrary constant, it doesn't make any difference. It will still be 0. So yeah, this is the case here. And actually for the initial, it really means that for example, if it is a second order ODE, so this is second order, the initial condition means if we know x of 0 equals to a number, just say x of 0, maybe 1, 2, or whatever number. Or maybe we also know x prime of 0, which means that the first derivative of x and then the value there, then x prime of 0. So if we know these two numbers, then we can determine C1 and C2 by, for example, if we just plug in 0 there, then exponential to 0 maybe 1. So you'll get C1 plus C2 and then plus this thing. Okay, if this is 0, then this term will vanish. Only plus this one equals to the initial condition. And then you take the derivative of this one and then plug in 0 and then equals to another one. So you still get two unknown with two equation, and then you may be able to solve for the complete solution, solve for the unique complete solution. Here we have infinite many complete solution. So for any number of C1 and C2, they are all the equation of this one. But if you have the initial condition, then you can determine the unique complete solution. Okay, so just now is just the easiest case, the polynomial. So if you have nth order polynomial, the particular solution is also an nth order polynomial. If it is a zero order polynomial, which means if g of t is a constant, then the particular solution is also a constant. Okay, so so the second case is if g of t is an exponential function. Which means that if it is exponential to alpha t, or maybe just multiplied by another constant, then we can also assume the particular solution to be with the same form, exponential to alpha t times a constant. So just that easy. Just need to remember this thing. Okay, so this is the second case. Which means it's the second case. And also we also talk about for the fourth case, which means that if g of t is a polynomial multiplied by an exponential function, then just like this one, this is an nth order polynomial multiplied by the exponential function, then we can assume the particular solution to be also a nth order polynomial multiplied by the same exponential. Just that trivial. Okay, so here is an example. The left side is the same form, and then on the right side, this is the polynomial times first order. This is first order polynomial multiplied by an exponential function. So so first you still need to solve for the homogeneous solution, which is the same as the previous slide. And then for the particular solution, it should be a first order polynomial multiplied by exponential to 2t. So we have the constant multiplied by exponential to 2t plus b times t times exponential to 2t. So if you just factor out exponential to 2t, you will get a plus bt, which is a first order polynomial of t. Okay, so here we just plug in this one back to equation 2. Okay, so we get this one double prime minus 2, this one prime minus 3 times this function equals this one here. Okay, so so taking the derivative of this one is need more work. Okay, for this one is okay. Taking the first derivative of this one is 2 times a times exponential to 2t, and then second derivative will be 4. So because we have the chain rule, so this 2 will come out. If it is second derivative, you have 2 squared in the front, which means 4a. And then for this one is more complicated because we have the product rule. T is a function of t, exponential to 2t is another function of t. So taking the second derivative will be like second derivative of this one and then times this function. So which will be 0 because t is the first order. Taking the second derivative will be 0. So and then 2 times the first derivative of this one and then 2 times the first derivative of this one. So it will become 4b exponential to 2t, which is this one. And then you also have the second derivative of this one multiplied by t, so which becomes this one. Okay, and then similarly for here, okay, this one go to here, this one go to these two terms, and then this one is here, this one is here. Okay, equals to 6t exponential to 2t. And then similarly, we collect the similar term. And before doing that, we can have some cancellation because here we have 4a exponential to 2t. And then this is also 4a exponential to 2t. So this one and this one can cancel. And then here we have 4b t times exponential to 2t, which is this one. And then here we have 2b exponential to 2t, and then multiply by 2. So we have negative 4b. And then we also have this one, minus 3 multiplied by this one. So we have minus 3b. And then we can have 4a. 4a is here, minus 4a is here, and then 4b here, and then minus 2b, and then minus 3a. So we just collect the term. We just factor out this one, and then equal to this one. Okay, so here, this is a first order polynomial without the constant term, but here we still need to plus 0 here. So we can collect the, we can compare the coefficient of the first order and the 0 order so that we can get two equations. So which means that for this one, which is this one, so 6 equals to this one. So we get the first equation. And then for this one equal to 0, we get the second equation. So here still we have two equations with two unknown, and then we can solve A and B. Then we can just plug it back to here. And then finally the complete solution is the homogeneous solution plus the particular solution. So this is for the second and the fourth case. And then finally, we will talk about the sinusoidal and then these two variation. Okay, so here it says if g of t is a sinusoidal function, which means that it can be sine of beta t and or cosine beta t. Maybe we only have sine of beta t. Maybe we only have cosine of beta t. Maybe they just occur together, because in high school trigonometry, you should know if you have something like a cosine beta t plus b sine of beta t, you can always write it as r cosine beta t plus phi, something like this. Okay, so this cosine has the same frequency of these two. Okay, just what I've mentioned. If a sinusoidal function enter a linear system, the only difference is that the output amplitude may change or the output phase may change, but it will keep the same frequency. So beta is the angular frequency here. Okay. So yeah, in high school trigonometry, you should know how to determine R. R should be like a square root of a squared plus b squared, and then yeah, you can just make it like R, and then cosine beta t cosine phi, and then minus sine of beta t sine of phi, something like this, and then you can just compare the coefficient, because you have cosine beta t, and then you get r cosine phi equals to a, and then r sine phi equals to b, negative r sine phi equals to b, something like this. You can always do this. And then these two variations, just for completeness, actually in the real situation, maybe this one still occurred sometime. Yeah, maybe this one, but for this one, I think it is seldomly occurred, but yeah, just let you know in your mind, if you have a polynomial times exponential times sinusoidal, you can get this. Okay, so back to the first case. If we have a sinusoidal function as the input, maybe this one, or both, then you just assume the particular solution to be a times cosine of beta t plus b sine the sine of beta t. So if you just get one, you still assume 2. If you have 2, you still assume 2. Okay, so yeah, so this is the sinusoidal function, which yeah, usually we will use this case. And the second case is exponential times sinusoidal. So you can expect we can also assume the particular solution to be the same exponential multiplied by the linear combination of cosine beta t and sine of beta t. And then if it is a polynomial times exponential times sinusoidal, so this is nth order polynomial times the exponential, and then times cosine and or sine. And then you can also assume the particular solution to be the nth order polynomial multiplied by the exponential to alpha t, and then also multiplied by cosine and sine. So we don't have a, b here because we already absorb a and b into the polynomial, so we don't write a, b there. Okay, so looks complicated, so let's just take a look at an example. So this is the simplest one. We only have a sinusoidal here for this linear ODE. So yes, so this is a little bit different. So the first step is to find the homogeneous solution, which means that we have a s squared minus s plus 1 equals 0. Okay, so this one, b squared minus 4ac is negative. Okay, so this one, so here we should have s equals 1/2, and then we have 1, and then plus or minus square root of 3, and then j here. Or maybe you can write as I, but usually I write as j. So here the real part is 1/2. The real part is 1/2. So we have a t over 2 exponential to t over 2 here. And then for the imaginary part, it is square root of 3 over 2. So we have cosine of square root of 3t over 2, and then sine of square root of 3t over 2. And then it is the linear combination of them, or multiplied by the exponential function. So this is the homogeneous solution. And then for the particular solution, it is sine of 3t. So we just assume the particular solution to be a cosine of 3t plus b sine of 3t. And then we plug in this one to equation 3, and then try to find the unknown coefficient a and b to be this one and this one. And then we can just plug it back to here. This is the particular solution. So finally, we have the homogeneous solution added with the particular solution with a and b here. So this is the complete solution. So I think it is quite, maybe the computation is quite complicated, but just need to follow the step and then you will get the answer. But maybe it needs some sort of practice, then you can familiar with it. Okay, so far we have already talked about how to solve the most common linear constant coefficient ODE, but so far there will be a glitch here. So for some specific ODE, the method just mentioned might have some problem. So let's see what is the problem. So here's an example to see what really is the problem. Okay, so here we have, this is a second order ODE, and then on the right side exponential function. Okay, so the first step is still to find the homogeneous solution first. Maybe you will have curious why we need to always find the homogeneous solution first. Maybe you feel like it's not so necessary, but for this one, you will get some problem. If you don't find the homogeneous solution first, and then you look at the particular solution, you may feel that, I can just assume xp of t to be a times exponential to t, and then plug it back to here. Then you will find problem. And here we see why. So first, we try to find the homogeneous solution. So this is second derivative, and then first derivative, and then original solution. So the characteristic equation is s squared minus 5s plus 4 equals 0. So you can quickly get that s is 1 or 4. S is 1 or 4. So which means that the homogeneous solution is c1 times exponential to t plus c2 times exponential to 4t. Okay, so if you are clever enough, you already know, okay, you maybe recognize that, okay, this This is exponential to t. This is also exponential to t. Okay, so you should be able to imagine that if I just plug in this one to the left side, it should give you 0. It should give you 0 because yeah, s equals 1 is a solution to the characteristic equation. So if you just plug in this one there, it should give you 0 because this one gives you 0. This one gives you 0. This one and this one are actually the same. So it will give you 0. Then you may not be able to find a such that the right side, such that the left side is 8 times exponential to t. So this is a problem. Okay, so here, I tell you that what we need to do next. If we find that this exponential and this exponential are the same, then for the particular solution, we should change it to a times t times exponential to t. A times t times exponential to t, like here. A times t. So we need this t. We need this t. The reason is just similar to here. It's just similar to here. When we find these two roots are the same, then one of it you should multiply by t. Similar for this one, you should have another t multiplied to there. Okay, and substitute it into 4, then we can find a to be blah blah blah, and then you can find the solution should be, this is the homogeneous solution, and then this is the particular solution. So we have an additional t there. Okay, so if you don't believe why, then we can just demonstrating it. Why it will be like that. It is x double prime minus x prime plus 4x equals how much? 8 times exponential to t. Okay, so here if you only know it should be related to exponential to t. So let's try xp of t should be let's say h of t multiplied by exponential to t. Okay, we don't know whether it is t yet, so let's just make it as a unknown function to find out it, and then it multiply with the exponential to t because it should be related to exponential to t. Okay, so here we just plug in to here, so we will get h of t and then times exponential to t and then double prime minus 5 h of t and then exponential to t prime and then plus 4 h of t times exponential to t equals 8 exponential to t. Okay, so here we have h double prime of t and then exponential to t and then plus 2 h prime of t and then exponential to t. The first derivative of exponential to t is still the same thing, and then we have a second derivative of this one, so we have h of t times exponential to t and then minus 5, and then the first derivative of this one is h prime of t and then exponential to t and then minus 5, the first derivative of this one, so we have 5h of t and then exponential to t and then plus 4h of t exponential to t equals 8 times exponential to t. Okay, so here let's see whether we can have some cancellation. So this is h of t exponential to t. This is 5 times that and then plus 4. So these 3 terms will cancel each other. Okay, so here we can just also cancel exponential to t. Maybe we can just divide exponential to t on both sides. So exponential to t will cancel. Okay, so here we have h double prime of t, and then here we have 2h prime of t minus 5h prime of t, which means that it is a negative 3 times h prime of t equals 0. So what is it? This is another constant coefficient linear ODE. Okay, so here if we try to solve it, so h double prime of t becomes s squared, and then this one become 3s equals 0, which means that s equals 0 or 3, which means that for this one h of t should be a times exponential to 0t plus b times exponential to 3t, like this. Yeah. Or maybe we can do another thing. Is like we just integrate on both sides. Which means that actually we can just integrate both sides. So for the left side we have second derivative, first derivative. So it turns out to be h prime of t minus 3ht, and then it is a constant. Maybe we can call it c. So for the left side is first order linear constant coefficient ODE. So it turns out to be s minus 3. So this is first derivative, we change it to s. This is original function, we change it to 1. So minus 3 equals 0. Okay, so here we have s equals 3, which means that h of t should be homogeneous solution should be like a times exponential to 3t. And then for the particular solution, this is a constant, so this should also be a constant. And actually just now we already have that. Yeah. Yeah, this is. Let me see. Yeah. So if we just plug in this one back to here, then we'll get x p of t to be plus 2 h prime t minus 3. Okay, so it becomes something like a exponential to 3t plus b exponential to t. This is a bit strange. I just forgot here here we have an 8 there. So here it should be an 8. Okay, here it should be an 8. So when we do the integration, we should have c plus 80. C plus 80. So in that sense, we should get plus something like ct plus ct exponential to t. Okay, so you see this term will occur. So that's why we should get t multiplied to the original function. This is our original one, so yeah, this will turns out to be 0 if we just plug in b times exponential to t into the original function. On the left side, it turns out to be 0, but here we should get this one. Okay, so that's why we need to multiply a t there. So you don't necessarily need to go through the step, but just have some sense that, okay, so if this exponential to t is the same as that one, so then we need to multiply a t to the function. And there are some other similar case, just like if for example, if just say let me see. For example, if it is x double prime plus x prime plus 1 equals something. Okay, so when you try to solve for the homogeneous solution, it is s squared plus s plus 1 equals 0. So the solution will be s equals 1/2 and then -1 plus or minus square root of 3j. So which means that if for the right hand side is something like negative exponential to t over 2 and then cosine square root of 3 over 2t. If it is something like this, a times this function, then you will quickly see that if you just assume that the function is exponential to negative t over 2 and then cosine times a and then plus sine times b, and then you plug in back to the left side, it will be 0. Then in that case, you also need to assume the particular solution to be t times exponential to negative t over 2 and then a cosine square root of 2t plus b times sine square root of 3 over 2t. Okay, so you need to make it one order higher. Okay, so but this is a special case. It don't really occur frequently, but that is the glitch you should know. Sometimes it might occur, and then you should know what you should do later. Although the calculation might be quite complicated. Okay, so finally we talk about the initial value problem. So which means that if we have a ODE and then with the initial condition, just as I mentioned, this is a second order. You should have the 0 order initial and then the first order initial. So you get 2 initial conditions for the second order linear ODE. Then you can be able to solve C1 and C2. Okay, so the previous step is just similar. So for the first step, you just find the homogeneous solution. So you just left the right side to be 0, and then you get this one, because it is something like s squared plus 1 equals 0. So s is plus or minus j. Plus or minus j means the real part is 0. So exponential to 0t is 1. And then for the imaginary part is 1, so you have cosine t and then sine t. And then here, this is first order polynomial. So this is first order polynomial plus sinusoidal of t, sine of t. So we have cosine of t and then sine of t and its combination. Okay, so the crucial thing is that this is cosine of t, this is sine of t. So if we just assume it to be c times cosine of t plus a d times t times sine of t, then you will get a 0. So in this case, you also need to multiply by t. And then you plug this one back to the original function, equation 5. Okay, so you get this one double prime plus this one and then equals this one. And then you can do some simplification, collect the similar term. So you get this is the polynomial, this is the cosine, this is sine, cosine, and sine. And then you compare the coefficients. So you get a equals 0, b equals 4, and then negative 2d equals 0, negative 2d equals 10. So turns out to be very simple. You don't need to solve complicated joint equation. So yeah, this is the coefficient for the particular solution, and then you plug it back to here. So here the complete solution is c1 cosine t plus c2 sine of t plus 4t minus 5t times cosine of t. Okay, so if we don't have the initial value, then it is done. However, if we have the initial value, which is so-called the initial value problem, then we need to move forward, which means that we know x of 0 equals 5. So which means that you can just plug in 0 to the original function. Then blah blah blah, the cosine of 0 is 1, sine of 0 is 0. Oh, this is 0, this is also 0. So it turns out that c1 equals 5. And then you also need to find the first derivative. So you just take the first derivative, you will get x prime of t to be this one. And then you plug in 0 to here. So you get x prime of 0 to be negative c times sine of 0 plus c times cosine of 0 plus 4 minus 5 cosine of 0 plus 5 times 0 times sine of 0 equals 1. So it turns out to be c2 equals 2. So which means that if we have the initial values, then we will get the unique complete solution like this. Okay, so yeah.